What up, y'all? This is Mr. Bergman here, section 7.1, graphing exponential functions. Let's do a little bit of review, right? So 2 times itself 4 times is 16. 2 times itself 3 times is 8. 2 times itself 2 times is 4. And 2 times itself only 1 time is 2. If you wanted to continue this pattern, you'd have to the left, you'd have to divide by 2 every time. Divide by 2, divide by 2, divide by 2. So what's 2 divided by 2? It's 1. And if you wanted to continue the pattern into negative exponent land, you have to keep on dividing by 2. You got a whole pizza, divided by 2, you get 1/2 a pizza. Divided by 2 again, you get 1/4 of a pizza. Divided by 2 again, you get 1/8 of a pizza. Divided by 2 again, you get 1/16 of a pizza. Notice 2 to the negative 2, 2 to the negative 3, compare that to 2 to the positive 3. That 2 to the positive 3 is 8, 2 to the negative 3 is 1/8. 2 to the positive 4th is 16, 2 to the negative 4th is 1/16. These are all positive numbers, 1/16, 1/8. You still have a positive amount of pizza, but they are reciprocals. They're fractions. If you keep on going 2 to the negative 5th, negative 6th, negative 7th, negative 10th, negative 100th, negative 1,000th, negative millionth, if you keep on cutting that pizza a million times in half, theoretically, mathematically, you'll have a very small amount of pizza, but you won't have zero pizza. And every time you cut it in half, theoretically, or every time you divide a fraction by 2, you'll never get 0. You'll just keep on getting closer and closer to 0. So we can say that it approaches but never equals 0. Big idea here is that negative exponents are related to fractions and reciprocals. And if you wanted to keep on going in the positive direction, it goes to positive infinity. Quick review on transformations. Inside is horizontal, outside is vertical. Plus or minus is a shift, and multiply or divide is some kind of a dilation. So the big question for today is what happens when you put a variable in the exponent? So the input is going to be an exponent, and the output is going to be a power. What do I mean by that? What I mean is this right here in green. I'll start off with larger numbers here. So if 2 is the x value, that means 2 is going to go into this function. 2 to the x is going to be 2 to the 2, which is 4. 2 to the 1 is 2. The input is an exponent. The input variable here is an exponent. You can see it's right there. Boom, exponent. So 2 to the 0 is 1. 2 to the negative 1, we've already said, is 1/2 and 1/4. It's going to keep on going. If you extend the table into the negative 3, negative 4, it'll go to 1/8, 1/16, 1/32. And it's going to keep on getting smaller and smaller and smaller, but it'll approach but never reach 0 as x goes to negative infinity. As x goes to positive infinity, yeah, these are going to keep on doubling these numbers, and it'll get as large as you want. What does that look like on the graph? It looks like this. You can see that these numbers are getting twice as high as the previous ones, but they will keep on going closer and closer to the x-axis. This dotted line represents what we're going to call an asymptote. Say it with me, asymptote. Yeah, it's a fun word to say, asymptote. So it's along the x-axis, and it's meant to represent the idea that you're going to just keep on going. I'm going to zoom in. Can I zoom in? I should be able to zoom in. Look at this. I'm zooming in. That graph is getting incredibly close, but will never actually reach. Zoom in, zoom in. You see how close I am zoomed in? There's still distance here. Anyway, this dotted line is meant to represent the idea that the graph will get as close to but never actually touch the dotted line. Let's take it back to the red. So let's say we had f of x is equal to 2 to the x plus 1. 2 to the x plus 1. So you would first evaluate the exponent, and then you'd add 1 to it. So you get all the same numbers you got before, except you'd be adding 1. Notice that all the y values are 1 unit higher. So 2 squared is 4 plus 1 is 5. 2 to the first is 2 plus 1 is 3. 2 to the 0 is 1 plus 1 is 2. 2 to the negative 1/2 is, 2 to the negative 1 is 1/2. And when you add 1 to that, you get 3/2. 2 to the negative 2 is 1/4 plus 4/4 is 5/4. So here, these numbers are all going to keep on getting closer and closer numerically to the value of 1. It'll approach 1 but never actually reach it. Let's see what this looks like. The red graph looks like this. Yeah, I want that. I want it to be red, dotted. And here's our red points. And now we're going to make this plus 1. So you can see this is plus 1. Everything gets shifted vertically up 1 unit because the plus 1 is on the outside. It's the same graph as before, except everything, including the asymptote, gets shifted up 1 unit. Let's see. And if we wanted to do the blue, it would look like this also. Go ahead and make sure that you copy the graph down. It doesn't have to be perfect, but let's make sure you do at least the green. The green would be best because that's the parent function. The red is just a transformation. The blue is actually also a transformation. Notice this is 2 times all this. That's outside. It's going to be vertical, and multiply or divide means it's a dilation. Vertical dilation by a factor of 2. Excuse me. All the y values are going to be doubled. So this used to be 4, and now it's times 2. It's 8. So 2 to the first, it used to be 2, but when you multiply it by 2, you get 4. All the blue values are going to be twice as high as all the green values from the parent function. But still, if you keep on cutting it in half, eventually you're going to eventually get to as close as you want to 0. As x gets more and more negative, the function will get closer and closer to 0. It approaches 0, but never actually reaches it. Let's do a few more of these. I'm going to change up the base a little bit. Everything above was base 2. Now we're going to look at base 3. So, meaning, here, this is f of x is equal to 3 to the x. This is 3 squared. The input is 2, so it's going to be 3 squared, which is 9. 3 to the first power is 3. 3 to the 0 power is 1. And, of course, anything to the 0 power is going to be equal to 1. If we want to keep on the pattern, doing the pattern, we're going to divide not by 2 this time, but by 3. So 9 divided by 3 is 3. 3 divided by 3 is 1. Cut that pizza into thirds. Cut that third of a pizza by 3. You get 1/9. Keep on going. 1/27, 1 over 81, 1 over 243. It's going to keep on getting smaller and smaller. It'll never reach 0, but it'll get as close as you want to 0. So we say, the helpful word we're using here is approaches. Run it back in the other direction. As x gets larger and larger and goes to positive infinity, so does the function itself. The y value is going to get as large as you want. What does that look like on the graph? Why, it looks like this. I'm going to make it green again. Green. This is what the parent function is going to look like. Green. We'll bring that back down here to 0. Put it back as just 3 to the x. You can see it's a lot steeper. It goes not 1, 2, 4, but 1, 3, 9. So all these points are going to be higher, and all these points are going to be lower. But it's still a very similar structure in that you've got an asymptote right here along the x-axis. Again, you could zoom in if you wanted to and just get as close as you want to that x-axis. Let's see. I'll bet you we can still see some distance between the two. Yeah, you see there's still a distance here, and if you go left, it'll drop down, and you can get as close as you want to 0 without actually getting there. Let's see. Boom. Good. So let's head back. Red. Okay, so this -1 is going to be inside the function. That means it's going to be horizontal, and the -1 means it's a shift of +1. Remember, we have to take the opposite of what we see on the inside. So all these numbers are going to be the same, except it's going to be a horizontal shift. Let's see, if the input is 2, 2 minus 1 is 1, and so 3 to the 1 is 3. 1 minus 1 is 0, 3 to the 0 is 1. 0 minus 1 is -1, that becomes 3 to the -1 is 1/3. Remember, this is a positive number. It's not going to be, that is a reciprocal of what it would be if it were just positive here. This -1, I know negative is a -1 is a negative number, but -1 minus 1 is -2, so 3 to the -2 is actually +1/9. negative 2 minus 1 is negative 3, so 3 to the negative third is 1 over 27. These numbers are going to get incredibly small really fast, but they will never actually equal 0. They will approach it only. And you go in the positive direction, these numbers will get as large as you want as well, by making the x values as large as you want. What does that look like here? I'm going to do the same thing. I'm going to just compare f of, we'll call it g of x. G of x is equal to 3 raised to the x minus 1 minus parentheses x minus 1. You can see here it is 1 unit over. Let's see, g of x1. Let's make it purple. All the same, these are all to the left, 1 unit to the left. There's a horizontal, the horizontal shift is +1, so it's to the right. All these numbers are 1 unit shifted over, or 1 unit away. I should have made that red. Okay, so then this one over here is 3 to the negative x. This is a multiplication division on the inside, so that's going to be a horizontal dilation. 3 to the negative x. What does that look like? Boom. Whoa, horizontal dilation. It's a horizontal flip. All these numbers got flipped over to the other side. You can see all the fractions are down here, and all the integers are over here. That's because when you put in 2 to the here, it becomes 3 to the negative 2, and 3 to the negative 2 is a fraction, 1/9. Positive 1 as an input becomes negative 1 here, 3 to the negative 1 is 1/3. And even a negative 2, 3 to the negative of negative 2 is just 3 to the positive 2. The two negatives cancel out, and you have 3 squared is equal to 9. And so this is going to approach positive infinity, and as x approaches positive infinity, the y values are all going to approach 0. And so you can see the graph looks like this. Let's keep going. Don't stop now. What happens if you put not 2 but 1/2 in here as a function? So you see the x value, positive x values are always easier to work on first. So 2, when the x value is 2, then that's 1/2 squared is 1/4. When the x value is 1, that's 1/2 to the 1 is 1/2. When the x value is 0, 1/2 to the 0 is 1. Now here we have to start taking reciprocals. So when x is negative 1, then the power over here is negative 1, and we'll take the reciprocal of 1/2 to get 2. Here, negative 2, when x is negative 2, then that means we'll take the reciprocal, which is 2, and 2 squared is 4. You can see that as x gets more and more negative, these keep on doubling, and they'll eventually get to as high as you want. They go to infinity. But if x goes to positive infinity, then these numbers get very small and they approach 0. So let's take a look and see what that looks like. This is 1/2. And so we can see here, it's going to look very similar. It's just flipped around. As we saw before, this is all the fractions are over here and all the positive numbers are over here. Let's do the same thing, except let's just throw in a vertical shift. This -1 is on the outside, so a vertical shift is -1. Changing it to red. Changing it to red. Changing it to red. -1. It all gets shifted down. Even the asymptote should get shifted down as well, because it eventually approaches -1. As we can see here, it's going to get closer and closer and closer to -1 and actually approach it but never equal it. If we had outside of vertical dilation, then let's see, it would look like this. This is going to be in blue, and this is going to be in blue, and this is going to be in blue. This is the blue function. So it's not a -1 anymore. Not -1 anymore. It's going to be 2 times. So there it is. Compared to the original, it's going to be twice as high. It's going to be twice as steep. You can actually, yeah, so there it is. The blue asymptote and the green asymptote are in the same location. There's no vertical shifting going on. And when you go to graph this, your function is also going to have the same horizontal asymptote right here, unless there's a vertical shift that would change it, like in the red one. Red has a vertical shift, so then the whole graph, including the asymptote, goes down 1 unit. An asymptote is a line that helps describe a graph's end behavior if the function approaches but never reaches a value. Let's take a look at these. Let's talk about them individually. So here's the parent function, 2 to the x. If you had a c value or a d value here, those would be vertical dilations and shifts, and then a and b's on the inside would be horizontal dilations and shifts. They look like this: 2 to the x versus 1/2 to the x. They both have the same domain. All x values can be put in, and you get a y value out. However, the range is different. 2 to the x and 1/2 to the x, they're both going to have a range of 0 to infinity. The y values are never going to be negative for these functions. They're going to approach 0, but never actually reach 0. So that's why we have a parenthesis right here, because we're never actually going to reach 0. They pass the vertical line test? Yes. They pass the horizontal line test? Yes. Do they have any x-intercepts? No, they do not. They approach the x-axis, but they never actually touch it. Y-intercept. So when x is equal to 0, then the y-intercept will be what the y value is. And it's the same for both. As x approaches infinity, what happens here? The y values are all going to approach infinity. These right arrows mean approaches. As an x approaches infinity, for the 1/2 x, it's going to go to 0. As x approaches negative infinity, it's 0, and then positive infinity. Are they increasing or decreasing? Well, the y to the 2x is going to be increasing from negative infinity to infinity, but the y to the 1/2 x is going to be decreasing. And is there symmetry? No, there's no symmetry. Let's talk about buying shoes. If you had a really nice pair of, say, hiking boots, climbing boots, specialty shoes, $200 pair of shoes. These are really nice Nikes. I don't have to tell you that multiplying it by the number 1 will keep the price the same. It's $200 times 1 is still $200. But if you wanted to increase it by 1%, one thing you could do is you could actually multiply it by something that's slightly more than the number 1. It's 0.01 higher. So if you took 200 and multiplied by 1.02, you'd get 202. And that's actually a kind of a one-step way of increasing something by 1%. There's other ways of doing it, but they take 2 steps. If you can go look at this 2% and say, oh, all I really got to do is multiply it by 1.02, you can do that in one step. And this $204 is a 2% increase. 10% up, that would be multiplied by 1.10, or just 1.1, and you get a $210. Pause. I meant $220. Sorry about that. Okay, so, and if you wanted to do a percent decrease, you could do the same thing as well. You just multiply it by something by 1% less than 1. That's 0.99. And when you multiply that, you get $198. So you can see this is a 1% decrease. 2% decrease would be 0.98, and then 10% decrease would be just multiplied by 0.90. You get 180. A 20% decrease would be $200 times 0.80 to give you $160. This is what I call multiplying it by a growth factor. So it's a lot easier to do percent increase and decreases using growth factor. So here's an example. Suppose the club invests $5,000 into a CD that yields 3% interest every year. How much will they have in the account after 20 years? Well, one thing you could do is you could start with a $5,000 and then in the first year increase that by 3%. That means multiplying it by 1.03. Multiplied by 1.03, multiplied by 1 point on your calculator. It's actually kind of quick to do. You can multiply by 1.03 20 times. Did somebody order Inspire? Here we go. Let's calculate. So what we can do is we can say this is 5,000, enter, and then you're going to multiply that by 1.03. Multiplied by 1.03. So that's once, twice, 3 times, 4 times, 5 times, 6 times, 7 times, 8 times, 9 times, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. We've multiplied it by 1.03 20 times. Or, if you wanted to, you could just use an exponent. Check this out. If you just take 5,000, and you know that you're going to multiply 1.03 times itself 20 times, just use that exponent. That's what that is for. And you get the same number. There's the shortcut simplified version. 5,000 times 1.03 raised to the 20th, and get it in one by hitting enter once, and you get 9,030 and 56 cents. Let's do another one. And instead, let's do depreciation. Cars. The value of Jaden's car depreciates by approximately 15% each year after purchase. Jaden paid 28,000 15 years ago. How much is it worth now? So we got the 28,000. Let's go multiply that by, we have to multiply by something that's going to show that it's decreasing. So instead of 1.0 something, we're going to go 15% less than 1.0, which is 0.85 times, let's see, 28,000, and then we're going to times 0.85. Once, twice, 3 times, 4 times, 5, 6, 7, 8 times, 9 years, 10 years, 11 years, 12 years, 13 years, 14 years, 15 years. So it started out at 28,000, now it's worth a measly $2,445. So you could do that 15 times, multiply the 28,000 times 0.85, 0.85, 0.85, 15 times. Or if you wanted to, you could just do it in one step, 28,000 times 0.85 raised to the 15. And you get the same number. Here are the formulas. Exponential growth, if you have a final amount is equal to the principal amount, that's like the 28,000, times 1 plus r. So here's the 1 plus the rate is 3%. So this 1 plus r turns into the 1.03. 1 plus the rate written as a decimal. And then you can raise it to the t power. In this case, it was 20 years. So that's what that would look like. Decay is this very similar, except it's just subtraction. A is the final amount. P is the principal. Like here, it's 28,000 times 1 minus 0.15, 0.15 to get the 0.85. Raise that 15 times, and that's what you'd get here. 28,000 times 1 minus r, which gives you the 0.85. Raise to 15. Anyway, that's it. I just wanted to drop in the video that my favorite month of the year is the month of May. It's a great time of year to have a birthday. It's a lot of fun. The anticipation of summer is upon us, and Mother's Day and my daughter's birthday are also in the month of May. So I've always had a lot of fun in the month of May. I hope you do too. Tell me what your favorite month is when you get to class, and I'll see you later. Take care.